Okay. Are there any questions or comments? All right. Dan, do you know the office number for Rosita Alvarez?
I think it's 195 down.
All right, let me start with a few announcements. There's a homework due today. Got to pick up the solutions on the way. Do we have graded homeworks to be handed in?
I could check with him.
Okay, but you don't have it. Okay. I'll try to make sure that all of your homeworks that you've handed in is given back to you by next Wednesday. Last homework is these problems out of Oppenheim and Schaefer. It's due Monday, December 1, right after Thanksgiving, and it's due at 11 a.m. at Rosita Alvarez's office. The reason being is that we hit a Friday on Thanksgiving, and so and I don't want to. This is too many problems to be handed over on Wednesday before Thanksgiving. We'll post the solutions to it. Dan, you're gonna please make a note of this. You need to post the solution to this on Monday, December 1 at 11 on the web. So you can go to the class web site and print it. And I will also, we will also return your graded homework, this homework, on Wednesday, on lecture on Wednesday. So before Friday's second final or second exam, you will have your graded homework in your hand. You can see how you did, where you made mistakes, and where the issues were. So once again, the second exam is on Friday, December 5th. And do we have a room for it already assigned? Did you talk to? Sibley's taken. Okay. Did you check any other? Who do you talk to regarding that? Who? Okay. Could you look into that, and by next Wednesday, let me know what the issues are there. So we'll announce where it is, but the time is 9:30 to 11 in this room on December 5th. And it'll be a comprehensive exam for the whole course, with more emphasis, obviously, on the second half. Are there any questions or comments? Yeah.
Is it possible to bring a
A review
review session before?
session. Then could you have a review session, let's say, on Tuesday, December 2? When is your recitations? Tuesday and Wednesday. So which day would you rather have a review session?
I have to go out of town on Wednesday.
Out of town?
Well, not out of town, but away from campus for part of the exam.
Hold on. You're missing your recitation on Wednesday?
No, I think I'll be back for the rest of
Oh, okay, good.
Most of the days.
It's shot. So how about Tuesday having a review session? Okay, let's just announce that. Put that on the board. So there will be a review session. what time is your recitation on Tuesday?
2 to 3.
Okay. And which room is it?
It's in 93.
Corey?
Yeah.
Okay. Yeah.
Is it possible, like, to change your mind and make the exam open book?
No. No. You can bring the 2 sheets that I was talking about.
How about no sheets?
Huh?
How about no sheets?
More sheets? You can write on both sides. I don't think we have that many concepts in this, that many equations. Pardon?
Too many tables.
Yeah, I mean, my goal is that you know some of those properties by heart. No? Okay, any other questions or comments? Okay. Just to get an idea of the difficulty of this last homework, how many people spend more than 15 hours on it? Around that time. How many between 10 and 15? How many between 5 and 10? How many less than 5? Okay. All right, very good. Any other questions or comments? Okay, so let's get going. What we're going to talk about today is wrap up DCT and then start talking about FFT, which is the next chapter in the book. Actually, one of the other reasons I can't make the homework be due on Wednesday is because I don't think I can cover all of FFT today. So that's one of the primary reasons. So where we were on DCT was last time was we sort of talked about motivation for why we want to do DCT, and one of them was that if you use, can you maybe, thank you. Great, thank you. So one of them was that if we use discrete Fourier transform, because it's one period of discrete Fourier series, it's if you have a signal like x of n that looks like this, you first make it periodic, and then you take discrete Fourier series of it. And because there's 2 values, because the first value and the last value could be quite different, you have this sharp discontinuity here, and you get unnecessary or undesired high frequency component in your coefficients. And so in DCT, or at least DCT2, what you end up doing is you reflect the signal like this, and so you get this, and then you do periodic analysis or Fourier analysis on this, and therefore you get a lot less, a lot more smoother signal here and a lot less discontinuity, and so it has a better compaction property in that it has fewer high frequency coefficients, which means that you can throw away more high frequency coefficients and for your signal not to suffer too much. And we talked about the fact that transform coding is used in image processing and audio and all kinds of things. And the 2 things that people use in transform coding a lot is the fact that you want the 2 properties of transform coding that's attractive is that the transform coefficients are independent of each other, unlike pixel domain intensity where the pixels are correlated, and you have to make sure you've squeezed the correlation out in order to reduce the bandwidth, the bits needed for that image. For transform coding, you can under some mild assumptions, you can show that the transform coefficients are statistically independent of each other. And also the transform, like DCT, have a compaction property in that you can throw away a large percentage of the coefficient, and the signal still more or less remains intact. Okay. So this is the analysis and synthesis for DCT type 2. What I talked about last time was 2 proposals. One of them was like this, which is to compute. You can use DFT to compute DCT. One way is through these 3 steps, and then the other way is through these 1, 2, 3, 4 steps. And what I'm going to do right the first maybe 10 minutes of this lecture, maybe 15 minutes of this lecture is show, in fact, that taking these steps, using DFT results in computing DCT as defined here in this manner. And actually, the second proposal of another way of using DFT to do DCT exactly shows this symmetrizing or flipping property with the fact that you don't introduce any sharp discontinuities is shown in this second proposal, and you can see that that explains automatically why DCT is a better transform than DFT for compression. And then I'll show you some graphs to compare the compaction properties of DFT and DCT, and that's pretty much where we leave DCT and we move on to fast Fourier transform. So let me begin today's lecture by talking about discrete cosine transform and its relation to DFT. So in particular, I want to start off with proposal number 1, which is you start with x of n, which is an n-point sequence, and we're assuming that it's real. And then we take a 2n point DFT of that to get x of k. And then we take twice the real part of x of k times e to the minus j pi k over 2n. And that, I propose, is DCT type 2. And I put a question mark here because I haven't proven it to you, but that's what I'm going to try to do now. So proof of this this little derivation. So let's just start by taking x of n, starting with x of n, and taking a 2n point DFT of x of n in order to get x of k. So what is x of k then? What's the expression for x of k? Well, it's the summation from n equals 0 to capital n minus 1, because this is only an n-point sequence, x of n, e to the minus j 2 pi nk over, because we're taking a 2n point DFT, this has to be 2n. Okay? So that's the expression for this x of k. And so now let's multiply this x of k by e to the minus j e to the minus j pi k over 2n. So x of k times e to the minus j pi k over 2n. And what you get is the same summation, n equals 0 to n minus 1 of x of n, e to the minus j pi k. And now I can combine these two exponentials, and I get 2n plus 1. 2n from here, and then plus 1 from here, over 2n. And now let's take twice the real part of that. So twice the real part of this whole thing. And what do I get? Well, the real part of this is just cosine. So it's twice summation from n equals 0 to n minus 1, x of n, cosine pi k, 2n plus 1 over 2n. And so that's it. If you look at the definition from last time that we had for DCT, this was our definition for DCT, and this is what we got. If you compare these two things, you see that that this expression is exactly the same as XC2K. So this is XC2K. So that means QED. That means we just proved it. Okay. So that's one way of. So what does that mean pictorially? Where it means, or in terms of block diagram definition of. So this is equal to, let's just write it, twice the real part of x of k e to the minus j pi k over 2n. And so is equal to DCT. So pictorially what happens is you start with x of n, which is an n-point sequence. Then you pass it through a DFT box. You take a 2n point DFT. And that gives you x of k. and then you multiply it by e to the minus j pi k over 2n. And then you pass it through a box that takes the real part of that thing, and out comes x c2 of k. And that is the DCT. Okay? So that's one way of computing DFT, using DFT to compute DCT. Another way of doing the same thing, so aliter, meaning a different way of relating. Let me pause here. Are there any questions on this before I move on? Yeah, question.
So it seems like we're using twice the number of points as the DFT, is it?
We're not, actually. Why not? Let's see. If you look at the expression for it, this is defined for k between 0 and n. So when I take the real part, I keep the first n numbers of it and not 2n numbers. Okay? Now, you bring up an interesting point. I do want to pursue that a little bit further. First of all, DCT is a real transform, right? So I started with n real numbers, and I ended up with n real numbers. If you were going to do DFT, if I start with n real numbers and do a DFT, I get n complex numbers. And each complex number has two real parts, right? The real part and the imaginary part. So somehow, it seems like when you're doing DFT, n real number goes in and 2n real number comes out. And when you're doing DCT, n real number goes in and n real number comes out. So does that mean that like DCT has some sort of a compaction property in that? No. No. Where's the trick? Where did I mislead you in this last minute of my... How did I trick you?
X of n is guaranteed to be even.
X of n what? No. X of n is any sequence. It can be even, odd, anything. But you're sort of on the right track. Huh? Exactly. You're right on. X of k, when I start with an endpoint sequence and I take its DFT, the final answer that I get x of k, it's true. It's n complex numbers, and each complex number has two real numbers in it. So you might think it's 2n real numbers, but it's not, because those x of k is complex conjugate because x of n was real. What does it mean for x of k to be complex conjugate? Well, it means that it doesn't have 2n independent real numbers in it. It only has n numbers. If I give you n numbers, if I give you half of it, you can build the other half, right? If I give it to you from k equals 0 to n over 2 minus 1, you can build the other half because it's conjugate symmetric. So there's only n over 2 complex independent numbers. The other n over 2 depend on the first half because the sequence was real to begin with. So both in the DFT case and DCT case, you start with n real quantities and you compute n other real quantities. It's just that with DCT, you start with n real numbers and you get n real numbers. With DFT, you start with n real numbers, n complex numbers that are complex conjugate, but okay? But because they're complex conjugate, the amount of information hasn't changed. Okay, is that point clear to everyone? Yeah? Yes, no? Yeah. And that, by the way, has its own sort of subtle advantages when it comes time to implementation. And what is that advantage? If you stare at this transform, versus like this transform. This involves complex arithmetic, and this involves real arithmetic. And so in some sense, your instruction set could be simpler if you don't have to do complex computation. I don't know how many of you have programmed in C. Unfortunately, a lot of the undergrads with DSP emphasis only program in MATLAB before they graduate, and that's not such a good thing. But in MATLAB, you can do complex and real, and it just doesn't make any difference. It's such a high-level language, and it's so slow that besides being good for undergrad courses, it's almost good for nothing else. But in the real life, but when you want to program something in C, at least in my days, you had to define what complex computation is like. Is that still the case, Dan? Yeah. Is it for those of you who are C programmers? Yeah. So in a powerful language like C, which is like the most widely used language in technical community, you still have to define what complex computation is like. Complex multiplication do this, complex addition do that. It's not that big of a deal, but it just adds complexity. Complex numbers add complexity. So that's where I want to leave it now. Okay. So here it's still an endpoint DCT. All right. I take only the first n numbers of it. And you can see that even if you get two n numbers here, there is a relationship between the first half n and the other half n, because this thing has a relationship between the first n and the last n. I mean the first n over 2 and the last n over 2, right? Okay, so now, any other questions regarding all of this? Okay, so let's move on to another way of relating DFT to DCT, and that's more my favorite because it actually exposes this flipping and symmetrizing thing that I've been talking about since last lecture. It explicitly tells you how it does it and etc. Okay, so here my proposal is as follows. We're going to start with endpoint real sequence, just like before, x of n. I'm going to pad it with n zeros, and I get a new sequence, x sub 2n of n. And then I'm going to form a periodic sequence, which I call x sub 2 of n I'm sorry. It's x sub 2 tilde of n, and this tilde always periodicizes things, right? It's the periodic version of x2n of n plus the periodic version of x2n of minus n minus 1. And I'm going to plot this and how this looks and what this is doing. This is the flipping and symmetrizing thing, and I'll show that to you in just a second. But let me finish this up by writing the fourth step. And step number 4, I'm going to take a 2-endpoint DFT of 1 period of x2 of n. And that gives me x2 of k. And then I'm going to figure out how this x2 of k related. And then step number 5, that's still not the DCT. Okay. Step 5, what I'm going to do is I'm going to relate this x2 of k to the DCT, which I have always been calling xc2 of k. Okay. But before I do anything else, let me show you pictorially what's happening in all of these things, right? And I'm going to start on a new sheet because I think I'll have more room to plot everything. So let's start with just a x of n. Suppose that x of n consists of 4 points. 4, 3, 2, 1. Index is 0, 1, 2, 3. Then, based on what this recipe tells me, I have to pad it with n more zeros. So n in this case is 4, so I have to pad it with 4 more zeros to get x2 of n. So let's do that. So x2n of n as a function of n is 4, 3, 2, 1, and then 0, 0, 0, 0. 0, 1, 2, 3, 4, 5, 6, 7. That's all it's doing. Then I'm going to build this. I'm going to make x2n, which is this guy, periodic. And how would that look like? Well, it would look like x2n of n, periodicized. It will look like 4, 3, 2, 1, 0, 0, 0, 0, and then 4, 3, 2, 1, 0, 0, 0, 0, 4, 3, 2, 1, 0, 0, 0, 0. Okay? And then, next, coming back here, I'm going to plot, I already plotted this, I'm going to plot this other guy, x2n tilde, but as a function of minus n minus 1. So let's plot that. So this would be x of 2n of minus n minus 1 periodicized. So it's the same thing here as I just replace n with minus n minus 1. So what does that? So by the way, this thing, let's just be complete about it. It's 0, 0, 0, 0, 1, 2, 3, 4. Okay. So what's this thing? Well, it's x of 2n flipped over to make it minus n, and then pulled by one notch to make it by one notch to this way to the left to make the minus 1 thing happen. So flip over and shift by 1 this way. So what would it look like? It would be 4, 3, 2, 1, 0, 0, 0, 0, and then 0, 0, 0, 0, 1, 2, 3, 4, and then 0, 0, 0, 0, 1, 2, 3, 4, 0, 0, 0, 0, 1, 2, 2, 3, 4. God. Okay? And these are the indices 0, 1, 2, 3, 4, 5, 6, 7. And these are the indices for this guy 0, 1, 2, 3, 4, 5, 6, 7. So I have x tilde of 2n of n and x tilde 2n of minus n minus 1. And let's go here. Now I have to add these two guys up in order to get to x2 of n tilde. So x2 of n tilde is the summation of this guy and that guy. And now you see what I mean by flipping over and extending. So I have to add this sequence to that sequence. So at index 0, it's 4 plus 0. So I get 4. Here, 3 plus 0. 3, 2 plus 0. 2, 1 plus 0. 1. And now, index 4, it's 1 plus 0. So 1. And then 2 plus 0. 2. And then 3 plus 0. 3, and then 4 plus 0, 4. Okay? So that's exactly what's happening. I started with this, I flip this over, and now I get the continuation of it, and this is the smooth thing that we were talking about earlier, right? And the same thing just repeats itself. 4 plus, so I get 4, 3, 2, 1, 1, 2, 3, 4. 4, 3, 2, 1, 1, 2, 3, 4. And on and on and on. 4, 3, 2, 1, 1, 2, 3, 4. Okay? So that's my x2 of n. And what does this say? It says now take 2n point DFT of one period of that. So essentially what we're doing, we take one period of this guy, 0, 1, 2, 3, 4, 5, 6, 7. So that's one period of this guy. And we want to take a 2n point, i.e. an 8 point DFT of this. That's what it does, and then once you do that, you get this x2 of k, and then you have to get that x2 of k and relate that to xc2 of k. And I'll do the mathematics of how all of that works in just a second, but I wanted you to see pictorially what happens to this sequence x of n. First it becomes x2 of n with a bunch of padded zeros, then it becomes periodic, then I make x2 of n minus 1, which is the flipped, pushed that way version of it, then I add these two things up, and that's what this symmetric flip comes about. Yeah, question. Can you use the mic, please?
If you just take one period of the x2 of n tilde, the formula is somewhat similar to a type 1 linear phase system.
Yeah, it's along the same lines, right.
So is there any how that we can use the principle we learned in DCT applied to what we learned previously?
I mean, they're related, but they're both pretty simple concepts. So, but you're right. You're right. On purpose, we're symmetrizing it the same way as we symmetrize those linear filter type stuff. Okay. So let's now mathematically show that in what way. Let's go to the last step and let's say how is this x2 of k, which we obtained through this lengthy process here, how is this related to xc2 of k? So let's do that. So the question we want to ask is, how is x2 of k related to xc2 of k? Okay. So what is the expression for x2 of k? Come back here. What is the expression for so how can we do that? Well, can you zoom so that, great, thank you. I claim that x2 of k, let's write down the expression for x2 of k, okay? Before I even write that, let this x of k denote be just the 2n point DFT of x of n. Okay? That means start with x of n, padded with n zeros, and let be that. So how can I write x2 of k, which is the upshot here, in terms of x of k? Well, what is it? Well, x2 of k is one period of DFT of x2 of n, where x2 of n consists of this and consists of that. So it's DFT of one period of that plus DFT of one period of this, right? What's DFT of one period of that? It's just x of k, right? You look at what's happening. I'm starting with an n-point sequence x of n. I pad it with n zeros, I get x2 and n, right? And the 2n point DFT of x of n is x of k. 2n point DFT of this guy is also x of k. They're all the same thing, right? And all I'm doing here is making it periodic and then taking the DFT of it. And this is a 2n point periodic sequence. This is a 2n point sequence. This is a 2n point periodic sequence. This is another 2n point periodic sequence. I'm adding up these two periodic sequences, and I take DFT of one period of it. What is that? I'm taking DFT of that without periodicity, and I'm taking DFT of that without periodicity. What's the DFT of that? It's just x of k. This is nothing but x of n with n zeros added on top. That's the 2n point DFT of this. So that's just x of k because of this part. And what's this? Well, we can invoke DFT properties. First of all, n has been replaced with minus n, so we've got to do x complex conjugate k. Okay. And second of all, there's a minus 1 here, so I have to add an exponential, which is e to the j 2 pi k over 2n. Right? So I can, by inspection almost, I can write x2 of k in terms of x of k. And why didn't, you might think that there's a bit of stupidity going on. Why am I making them periodic, add them together, and then take 2n point DFT of one period? Why am I doing that? Anybody can, why am I torturing you guys by first making it periodic and then take one period? It doesn't seem like there's much point in, they cancel each other out. Well, because I want to be in the periodic domain because of the peculiar DFT properties, because this thing has got to, if I didn't do that and I just wrote x to n of minus n without any periodicities, then the region of support of x2 of n would be somewhere else. It would be negative values of n, and then the DFT thing will fall apart and all those other things. So the only reason I'm doing the periodicity thing is so that I'm kosher. Remember, DFT only works for indices between 0 and n or 0 and n minus 1. My sequence, my time domain sequence has to be in those regions. And by doing these periodicity games, I'm just ensuring that the region of support of everything is in the kosher area. It's between whatever the thing that's supposed to be. Okay? So in one shot, I could write down x2 of k as this. And now, let's continue the calculation and answer this question of how is x2 of k related to xc2 of k. I'm going to rewrite this as, by bringing the exponential out, factoring it out, it's e to the j pi k over 2n of x of k e to the minus j pi k over 2n plus complex conjugate of e to the j, x complex conjugate k, e to the j pi k 2n. Remember, this is 2 pi k 2n. Pi k 2n is here, and another pi k 2n is here. And why did I do that? The usual trick. I wanted these two things to become what? Complex conjugates of each other so that I can get something real out of it. So I get e to the j pi k over 2n twice the real part of x of k e to the k, x of k e to the minus j pi k over 2n. And what is twice the real part of that? We just did it as part of proposal number 1. Remember? This is proposal 1. Twice the real part of x of k e to the minus j. Remember, twice the real part of x of k e to the minus k 2 pi 2n. This quantity here is just xc2 of k. So that is xc2 of k because of proposal 1. So this x2 of k guy that we get is equal to this exponential times xc2 of k, but let's just multiply by the negative of that e to the j pi k over 2n. That is equal to xc2 of k. Okay? So if I compute x2 of k and I multiply by this exponential, I get my dct. So if I build, the bottom line is that the bottom line is this. I start with x of n, I pad it with 0, then I make a periodic sequence out of this guy with the padded sequence that looks like this. Then I take a DFT of one period of that, I get x2 of k, then I multiply by this exponential, and I get this. So in this picture, after I take the 2m point DFT of this sequence, remember this flipped over pictorially, all you have to do, you start with the sequence, you flip it over this way, you get a 2m point sequence, you take a DFT of that guy, and then just multiply by an exponential and take the first n numbers, and that is your DCT. So DCT is the DFT of the extended symmetric extension of the signal. This is called symmetric extension. You start with a signal, you symmetrically extend it, you take a 2-point DFT, multiply by exponential, and boom, that's the DCT. And that's exactly why DCT doesn't have very many high frequencies in it, because I did the symmetric extension. And why is there 4 kinds of DCTs? Because people could never agree how to symmetrically extend it. The same way as with type 1, type 2, there was like 4 different ways of doing the extension. There's also 4 different ways of extending this. So for example, you could anti-symmetrically do it. You could make 4, 3, 2, 1, and then make -1, -2, -3, -4. Or you could do or you could put a 0 in between and then add 1 more. There's lots of different ways you can extend it, but DCT part 2 is the simplest and easiest to understand. And all it involves is just flip it over and pad it. So it's the DFT of this extended sequence multiplied by some exponential that gives you DCT, and that's why it has nice, good compaction properties. And are there any questions on this? Just to wrap up this discussion, I'd like to show you a picture off of Oppenheim and Schaefer. Unfortunately, it's in the first edition of discrete time signal processing, not in the second one. I couldn't find it in the second one, so I'll just show it off of this one. But let me just find it. Sorry, the wrong way. This is your book. This is the thing you're using, right? It's off of this other book. Why am I confused? Which one are you guys using? This one. Okay, so it's in the other one. All right. You can tell that I'm not keeping track of things as I used to. Then I'm wrong. It's in the version that you have now, perhaps. Oh, here we go. It's in your own book. I was all wrong. Okay, so page 589. Why did I think that? When I made up this lecture, I said, oh, it's too bad. Oppenheim had it in the previous edition. How come he doesn't have it in the new edition? But in fact, I was wrong. He didn't have it in the old edition. He was in the new edition. Okay, so you have it all. What I want you to look at is figure 8.29. Okay. So if you so here's a nice plot that shows you what the compaction property is like. Okay, so you start with a number of, let's say, 32 point. You start with a with a 32-point sequence, okay? Yeah, and you compute the DFT of it, and you compute the DCT of it. And what you do is, and you repeat that over many, many cases, okay? Lots of 32-point sequences. And for each of these points on the x-axis, let's say for number 5 or number 10, let's say, you keep the first 10 coefficients of DCT, and you also keep the first 10 coefficients of DFT, and you throw away the rest. Throw away means you set it equal to 0. And then you take the inverse DFT or inverse DCT of the resulting thing and look at the error that was introduced by setting the by setting those coefficients equal to 0. Okay? So you start with 32-point sequences. In this case, keep 10, throw away 22, and take inverse transform and compute, see how much error got introduced into the signal, mean square error of introduced into the signal by doing that process. And the solid curve underneath here is DCT, and the dashed curve is DFT. Okay? So you can see that all the way to 25, which is the number of coefficients set to 0. If you set 25 coefficients equal to 0, in DCT, you almost introduced no error whatsoever at all. This is showing the superior compaction property of DCT over DFT. Okay? And only when you get to here, then you have a sharp increase. Just, when you get to 27 or something like that, then you get a sharp increase. And DCT and DFT behave the same towards the end. But for the most part, DCT preserves the energy so much better. In other words, you can throw away a lot of coefficients in DCT and see very little error in your time domain signal. And this plot is an expected curve. You've done it over a bunch of you have averaged it out over. You repeat this experiment over thousands of sequences. So it's a average type thing. If you take 290T, when we talk about compression next semester, we will also show another property of DCT, which is if your signal satisfies some certain statistical properties as a Markov type signal and has a certain correlation coefficient, etc., you can show that DCT comes close to the quote-unquote optimal transform. So you learn more about that in 290T. Okay, let me pause now. Are there any questions? So these are really that's really the fundamental reason to be switching over to DCT. And that's why it's used, as I said, in H.261, H.262, H.263, MPEG-1, MPEG-2, MPEG-3, MPEG-4, etc. Yeah.
From your last slide, did you say
in the writings?
at
This one.
the bottom of that page?
Uh-huh.
From the DFT, did you say from 2 endpoint DFT we have to pick endpoint DCT? Is that right?
Yeah, this is certainly a 2 endpoint sequence, but the first n of it is what we pick as this. You discard. And why is it that the first n? Because the other n is related to the first n. There's not that many degrees of freedom. These things are tightly coupled. And that's exactly why, the answer to your question as to why am I not allowing an open book exam or bringing you 5 sheets, these symmetry properties, and they're so fundamental. I really want you to be in your head. It should remain in your head for as many years as possible. Because the thing is, I know you're going to be using whatever MATLAB or equivalent of MATLAB or whatever signal processing packages to do design of things. For actual system implementation, you have to do C, but that's a separate issue. That's an implementation issue. But even when you use MATLAB, let alone when you write your own C program. Let's say I'm writing a C program. If I implemented DFT correctly, the first test I do is I give it a real sequence and see if my MATLAB program, with my C program, gives me complex conjugate answer. And if it doesn't, there is a bug. And for that, you don't want to get Oppenheimer and Schaefer and look up the table and say, oh, it was supposed to be conjugate symmetric. That has already to be in your head. It has to be sort of like second nature for you, that these properties hold true. When it's real, it's conjugate symmetric. When it's that, it does this. And again, you've seen it many, many times. You saw it in 20, you saw it in 120, and now sort of for the third time you're seeing it in 123. Any other questions? Yeah.
It's kind of funny why we actually do the second proposal that you said, because we actually don't get like some really clear relationship.
The only reason I did the second proposal is for the sake of that picture. I had claimed this flip thing, and this second proposal illustrates how that flip thing. Remember, I said when you take DFS, it's like you take x of n and you just periodically repeat it, and then that introduces high frequency. And then I said if you do that, it introduces less high frequency. The only reason I do the second proposal is to just justify that extension. Okay? I'm not proposing this as a computational thing. I'm just sort of justifying why DCT does well. Because it's the same as doing this DFT of this sequence, and therefore it produces less high frequencies, and that's shown in that plot that you just talked about. Any other questions? Yeah.
Why do we still use the DFT if there's something much better?
Well, DCT is just for a compaction property and compression, but for a lot of other applications, DFT is still pretty powerful when you want to do Fourier analysis, for example. So compression is one big example of DSP in one field that is used a lot, but there's other ones. Any other? And in fact, you know, a lot of these transforms, as you're seeing, they're very much related to each other. From this you can get to that, from that you can get to that. It's like a very connected graph, if you will. Okay. So what I like to do next is switch gears and talk about fast Fourier transform. And again, to get an understanding of what you guys know about it already, let me just do a quick show of hand. How many of you have seen fast Fourier transform in some other course or some other context? Really raise your hands. One. Okay. And I can see some of you guys were undergrads. Is that right? So, yeah? Was it covered in Gaspar's course, for example? He took it from Schering. Of the undergrads who took it with Gaspar, did he cover FFT? No, he did not. And the remaining people who raised their hand, how many are undergrads? If you're undergrad and saw FFT before. And where do you see that? 20. Okay. Okay. And how many people know what decimation in time is? 1, 2, 3, 4. And decimation in frequency, the same people probably. 1, 2, 3, 4. Okay. All right, so let's get going. Let's assume that we're covering it properly. Okay, so FFT, the good news is that, you know, this is not another transform. I mean, you probably have had it with transforms by now. It's just a way of computing DFT. FFT stands for fast Fourier transform. Actually, the second semester I was at MIT, I happened to run into my advisor, Al Oppenheim, in MIT's cafeteria, and he was with his, at that time, 4-year-old son, Jason. And so I sat down at their table and I was having lunch with them. And I said, Jason, what does your dad do? He said, he does FFTs. 4-year-old notion of what Oppenheim does is he does FFTs. Yeah. Yeah, actually, if you ask my son when he was 4 what I do, I don't think he would have said FFTs, but right. Okay. If FFTs had no applications to trains, he just wouldn't have any interest in it at all. Okay. It's not Fourier transforms, but just faster. That's another joke about FFT, but it's a way of computing DFT in a fast way. And why do we care about computing DFT in a fast way? Oh, there's all these stories I told you how to use DFT to do linear convolution, and convolution is an important thing to do LTI systems, all these other things. And by the way, people use FFT not only to compute DFT, but nowadays it's such a fast algorithm, they also use it to compute other transforms like wavelets and other things. So it's such a blessing to have these fast algorithms. Every time you run into computing a new transform that's so hard, you just hope and pray to relate it somehow to DFT, so then you can apply FFT, so you can get this new transform computed in a really fast way. Okay? So let's just write down what this thing means. So it's merely a way of computing DFT faster. And I understand, how many of you have taken CS170? Just 1 or 2. Did they cover FFT there? No. Oh, wow. No? And no? Wow, it used to be. When many years ago, I used to take this show of hand. A lot of the undergraduates took CS170. Anyway, the CS guys were very interested in DFT with FFT because it's called an embarrassingly parallel algorithm. In parallel processing, the goal is you have an algorithm and you want to parallelize it, and a lot of times you have to sweat and think hard and spend years coming up with a way of parallelizing an algorithm. But FFT it's called it. And then the algorithms that are just so obviously parallelizable are called embarrassingly parallelizable. And so this FFT is an example of it. And for years and years, when DARPA was funding parallel processing research, all the researchers at the end of like a 4-year study program, they will always come up with, oh, now we can do FFT on this parallel processor. And so for years, it was a toy example for those guys as well. So it's merely a way of computing DFT, and it's received a lot of attention because DFT is an important transform. It's used all over the place. But what you have to know, it's not a new transform. We're not talking about DCT or anything like that. And it comes in 2 flavors, okay? One of them is decimation in time. And I'll talk about that today. And then the other one is decimation in frequency. And we can come up with flow graphs for these 2. And what you'll see is that the flow graph for decimation in time is the transposed version of the flow graph for decimation in frequency. So remember the transposition theorem from flow graphs from the middle of the course when we're talking about realizations of filters, right? It comes in here as well. And again, the motivation for studying FFT is real-life systems. There's a lot of them that are LTI, or we model them with LTI. We want to do convolutions on them, and then we can use DFT to do convolutions, and then we can use FFT to do DFTs. Okay. So what is the definition of DFT? Well, the DFT is given by x of k. If I have an n-point sequence, x of k is summation from n equals 0 to n minus 1 x of n e to the minus j 2 pi n k over n. And that's for k in between n and 0. So, by the way, it's not only can only be used to do DFT, it can easily be used to do inverse DFT. And I think it's one of the homework assignments. Is you have a box that does DF. It's either a homework assignment or probably be in the final or something. If you have a box that does endpoint DFT of a sequence, what thing do I have to do to the input of that box to do inverse DFT of that number? No, no. One is forward DFT is this. The other one is e to the plus j. I think it's pretty trivial. You can. Yeah. That's the easier part. But you have to do some permutations of things. Or another one of my favorite problems is like I don't know, if you have a box that does one thing. What do you do to its input? To get it to that box to do something else. Those are very fun problems. So what do I mean by this is a way of computing DFT faster? The first way that when you stare at this thing, you say, wow, what do you mean? It's taking a number, multiply it by an exponential, add them all up, and you get the answer. That's the easy way of doing it. That's called direct computation, and that's the time-consuming or compute-intensive way of doing it. Let's just calculate how many operations you need for this direct computation. Okay? How much do we need? Well, for each k, I have to do what? n minus 1 adds. And when I say adds, I mean complex adds, right? Complex adds. And I have to do n complex mults. Okay, and how many values of k are there? There's n values of k. That means I have to do number of adds is n times n minus 1, which is approximately n squared, and number of mults is n squared. So it's about n squared, order of n squared computation. So if I double the length of my sequence, the computation time becomes what? 4 times larger. Okay? So it goes as a square. And in science and engineering and in computer science and DSP, we're always after what's called scalable algorithms, scalable techniques, where when the size of the thing goes up, you don't want things to go up exponentially, like square. You want, ideally, so this is called O of n squared, right? Ideally, you want everything to be what? O of 1. Yeah, exactly. That means whether you get a 10-point sequence or a 10 million point sequence, you get the same answer. What other application, by the way, is this scalability thing is important? It is used in real life a lot. Like, pardon? Headers? Adders. Like in circuits. Okay. So in my field, in video streaming, right, you have a server, and you want that server to be able to stream to millions of people. And the server algorithm has to be extremely simple so that I can maintain a million connection. And when you add another million connection, if 2 million people wanted to watch the same video off of the same server, you want the server to be able to handle that. So the complexity of each transaction has to be very, very small. Each streaming has to be very small for it to scale. And is it in real world, like when you go buy streaming servers from real networks? Does it go like that? No. I can tell you the price point. You pay for a dual Pentium machine, you can get it to stream, I don't know, 5,000 streams, each at 20 kilobits per second. And so if you get 5,000 more users, you need to get another dual Pentium, and then another dual Pentium, and another dual. So you just stack these things up, and then you have a load balancer in front of it as the requests come in to divide it up among these Pentiums to serve your video. So the name of the game in that thing is which company or which technology per each dual Pentium machine, which company can stream more bits, or more streams, or can pump more. They're just pumping machines. They just send bits out, right? So that's another thing where you want to keep things as scalable as possible. In general, you want to keep scalability. In general, it's very highly desirable to come up with algorithms that scale and solutions that scale. Another one is in networking. Okay. Why is it that, for example, all these reservation-based techniques for sending multimedia over networks, why is it that never worked? Because it can never scale. Why? The routers in the internet, they don't keep track of the flows. They don't say, oh, this is Avide's flow to Dan. Oh, okay, yeah, let's reserve it. Let's do that. And then because as the number of flows goes up, it becomes too complex to keep track of everything. So all of those RSVP-based things, in-serve things, a lot of solutions in networking have been set aside, never deployed on a wide-scale basis because they didn't scale. Think of the routers. What are the routers? Why is it that the internet has been such a huge success? Each router just looks at the beginning part of each packet and routes it immediately to the correct node. It has a lookup table, and boom, it goes. So there have been many fancy algorithms that have been proposed to replace the dumb first in, first out router out stuff that's in today's routers. And why is it that Cisco and Juniper and Redback and all these other guys don't implement it? Because they don't scale. Because the routers are processing gigapackets per second, especially in the backbone of the internet. It has to be blazingly fast. There's no time to have a fancy algorithm, oh, do that, and if it has that, do this, and look it up, and it has to be very simple, very scalable. So scalability is a notion that not only applies to algorithms, it applies to hardware like servers, it applies to routers. You want to have very scalable solutions. As the number of flows, as the number of users, as whatever that n is goes up, you want things to remain cool and down. Okay. So O of n squared, that's bad. What FFT in return promises you to do as an alternative to direct computation is to do n log n. Okay? So as an example, if n is 10 to the 6, if I have a million-point sequence, direct computation will give me O of 10 to the 12 operations, and FFT will give me something like 10 to the 6 log base 2 of 10 to the 6, which is approximately 2 times 10 to the 7. So if I compare these two things, there's about 5 orders of magnitude of difference. So something that could take 1 second using this, it could take 100,000 seconds. How much is that? That's 100, let's say, is 60, so it's about 1,000 minutes. Yeah, it takes about a day, half a day to a day. Yeah. So it's a difference between a second and a day, and that's important, especially if you're a grad student and you're trying to graduate. Well, what it is you have an idea, you want to test it, right? You program the thing up, you run it, and in one case, 1 second later, you know if the thing worked or not, right? In the other case, you wait a whole day before you know whether it worked or not. Of course, you guys have the advantage of having extremely fast machines that we didn't have at the time I was a grad student. I was working on trying to make some algorithm converge when I was a grad student, and the thing would just not converge, and it would take me a whole day just like this to find out whether it converged or not. And the joke was, everybody I ran into, I said, oh, if my algorithm doesn't converge, I'm going to jump off the bridge tonight. Of course, I never did. If I did, I wouldn't be here. Okay, so it's good to have fast answers. That's really, and if you're in industry as well, it's good to have the answers fast, because this thing is only a part of a much bigger algorithm. You're trying to figure out, I don't know, how to process the radar signal or the sonar signal or the medical signal, and you're in the algorithm development stage, and this is just one step of it. So one other note before we get going on FFT is that it was invented by Gauss in the 1800s. I think I've mentioned that many times before, and it's one of those classic stories that it didn't matter that he invented it. And what was he working on? He was working on analyzing periodic motion of the planets. Okay, so he came up with the FFT algorithm, but at his times there was no computational devices, so it didn't matter whether it was n squared, n log n. They're just all too slow. The people who revived it in 1963 or 2 were Cooley and Tukey, two scientists at IBM. I think I've mentioned that to you guys before. And what they really did is they just looked it up from what Gauss had done, and they reintroduced it to the technical community. And why is it that they could do that? Because finally in 63, I mean, I know it's very hard for you to believe, but compared to 50s, for example, finally in the 60s, some fast computation machines were being developed and designed and produced that could actually take advantage of n log n versus O of n squared. And they demonstrated that you could process signals a lot faster and do harmonic analysis using FFT. And by the way, the application that was very hot at that time, so the driver of a lot of these things was speech technology. Telephone companies were very interested in processing signals digitally. That was the time that the infrastructure in the U.S. was getting built. And so there's actually a whole lot of stories about, there's a whole set of historical studies about how, when the Bell Lab guys, that's the telephone company, found out that Cooley and Tukey have come up with FFT, they went through a series of tricks or steps to prevent IBM. Cooley and Tukey were working at IBM Watson Research Center in Yorktown Heights, but they went through a whole series of steps and manipulations and maneuvering to make sure that IBM doesn't file a patent on FFT, and that Bell Labs could use it freely for their building their telephone network. It was the thing that launched the field of digital signal processing in 1963. And if you think about it, around 1963-64, for example, was the time where a guy like Oppenheim, the author of this DSP book, got his PhD at MIT. So So him, together with Rabiner and Gold at Lincoln Labs, together with folks at Bell Labs, and together with IBM Yorktown Heights guys, that northeast corridor was sort of the birthplace of DSP and the applications. Again, was initially it was speech, and then quickly the government became interested in it because then you can do radar signal processing, sonar, defense applications blossomed. And of course, in the 80s, during the Reagan era, the defense industry was the main feeder of the field. But in the 90s, during Clinton era, the defense became less important, and other commercial applications sort of showed up. It remains to be seen what happens in 2000s. Okay, yeah, question.
I think they filed a patent on it. I mean, wasn't it invented by Gauss?
Yeah, I think I don't know the legality of it, but I think the way it worked is, I think they invited them to go to Princeton, New Jersey, to give a talk or something, and somehow through that Princeton connection, you know, the Bell Labs is also very close to Princeton. It's Homedale, New Jersey. I have to look. I have heard this before. I can't remember the details of it, but they went through a lot of tricks to just make sure it's publicly available and make sure no patent gets filed. By the way, Bell Labs and IBM Watson Research Center, you know, at the time when I was getting my PhD, like 15 years ago, those were the two premium places that, or premier places that PhDs would go to. Like if you said somebody, I'm studying for my PhD, I said, oh, yeah, you're probably going to go to either IBM or Bell Labs. You know, that was the thinking. I don't know, and since then, they have sort of disassembled. Bell Labs doesn't exist, right? It got split between Lucent and AT&T, and you know, Lucent does the switches and stuff for networks, and AT&T is the guys you pay your money to for your long distance thing, but neither one is doing very well, and they've laid off a lot of their research people. I mean, at least in video and DSP, all the groups in that area have been canceled, and people have left to academic jobs. So for people getting PhD nowadays, and correct me, we must have some grad students from EECS here. It's not. I'm hoping that you're not getting a PhD to go to IBM and Bell Labs, because Bell Labs doesn't exist. IBM Watson Research Center still does exist. Cooley and Tukey have obviously retired, but IBM has also gone through a lot of restructuring. I know at Almaden, which is the closer thing to Berkeley, Nobel laureates have lost their job. The physical sciences department there have just been annihilated, almost nothing left. And to the extent, as I said, I know of some Nobel laureate guys who just don't have a job there anymore. But Watson still is there. I worked there as at the summer of one of my undergraduate years, and yeah. At that time, by the way, when I worked there, it was 1981, and there was a bunch of other summer interns, and the joke was, you know, at that time, who used to make PCs? IBM was it. There was no Dell, there was no Gateway, there was no HP, none of that. It was just IBM, and the joke among all the summer interns was the biggest company who makes computers in the world doesn't know how to program it, and it was very true. You know, the hardware was there, they knew how to design computers, but the software wasn't there. And guess what happened next? Microsoft came, they wrote software for IBM machines, then they took over, and then one thing led to the other, and that's the way things are today. There's no more IBM computers, right? You buy PCs from IBM? Almost none. Maybe you buy ThinkPads that are laptops, but it has become a sort of a commodity. But IBM is the company that invented PCs. It was just invented there, but they didn't know how to write programs for it. They never provided good software to entice people. I knew a whole lot of people, like in the early 80s, their job would say, "What do you do?" He said, "I'm selling IBM PCs to people." And I bet you none of them are in business today. Well, not only today, but then it wasn't a good business because it was a very hard sell. And that's exactly the gap Microsoft came and took over, took advantage of. It said, "Look, there's this machine, nobody ever does anything with it, and we can write software for it and make something productive out of it." And that's, you know, one thing led to the other. I think that's enough of stories. So Yeah, good thing the homework is due on Monday. On Wednesday, so this is chapter 9 that we're covering now. I'll go over decimation in time and frequency.